So are you still making those volcanoes with baking soda for your science exhibition and experiments? So this still model is for you. This is a still model of black hole which I've made here, and this explains the fundamental concepts of black hole and phenomena happening in there. So these two small objects are called, this one is called neutron star and this one is called white dwarf. So before getting into the parts and functions and phenomena of black hole, let us understand how black holes are formed. Every star is in a constant battle, gravity pulling inward and energy pushing outward. But when the fuel runs out, gravity wins. If the star is small, like our sun, it doesn't become a black hole. Instead, it shrinks into a white dwarf, a dense, Earth sized object still glowing with leftover heat. But if the star is much bigger, things get intense. It explodes in a supernova, one of the most powerful events in the universe. So, if you ask what's left behind, it's a neutron star. Incredible dense, just one teaspoon of it would weigh billions of tons. Now, here's where it gets extreme. If the star is massive enough, even neutron stars can't hold it up. Gravity crushes everything into a single point. This creates a black hole. By the way, I have also made a video about simulating black holes in Python. So if you are a person who genuinely likes coding and astronomy, you can check that video out. It is very interesting and very unique. So let's get into the topic. This is the still model of black hole and it got various parts in it. So let me explain it one by one to you. So this is the singularity. The singularity is the point where all the mass is concentrated, and this is just an imaginary point and we don't know what exists there because light can't even escape from it, as we already know. So the next part is the golden disk. It's actually an imaginary line. This imaginary line is called the event horizon. The event horizon is a point which an object enters, it can't escape from a black hole. So it is the point which have no return. So the next part is the accretion disk. The accretion is nothing but the dust. The dust swirling around the black hole because of the gravity, and it is where the intense heat is produced because of the friction between the dust particles. So these are all the parts of gravity, and let me explain the phenomena that are happening in the gravity next. What if space could bend light like a lens? In space, massive objects don't just sit there, they actually bend the fabric of space-time. This idea comes from Albert Einstein's theory of relativity. When light passes near something extremely massive like a galaxy or a black hole, its path curves instead of moving straight. This bending of light acts as like a cosmic magnifying glass. It can stretch, distort, or even duplicate the image of distant objects. Sometimes it creates glowing arcs or even a perfect circle called an Einstein ring. Gravitational lensing helps scientists to see galaxies that are too far or too faint. It also reveals invisible things like dark matter. Near a black hole, the effect becomes extreme. Light can loop around it, showing multiple images of the same object. So this is our model, and how we're gonna mention the gravitational lensing to the viewer is like that. We added two paper slips. Two paper slips being added to the back of the black hole, accretion disk of the black hole, and when light travels through the black hole, it gets bent and forms something image like this. Because of the light rays getting bent and going straight, the image obtained of the accretion disk back of the black hole will be like this. Same goes to the accretion disk below, and it gets bent through the black hole's gravity and goes straight, and because of that, the image would something look like this. This is the image that we see in the NASA simulation, and also the real image of the black hole. So this is how we get the image of the black hole because of the gravitational lensing. So this is how gravitational lensing works, and you can explain it by this black hole's model. Furthermore, this is the formula for gravitational lensing, and this formula calculates the deflection of angle caused by a celestial object like a black hole or a neutron star. What if 1 hour felt like 7 years on Earth? This is gravitational time dilation, predicted by Albert Einstein. The stronger the gravity, the slower the time moves. In Interstellar, astronauts land on a planet near a massive black hole called Gargantua. Because of its extreme gravity, 1 hour on the planet will be equal to 7 years on Earth. A black hole bends spacetime so intensely that time itself slows down. The closer you are to it, the more stretched time becomes. This isn't just movie magic. The science in Interstellar was guided by physicist Kip Thorne, making it one of the most accurate depictions ever. Near a black hole, seconds for you could mean years far away. You wouldn't feel anything strange, but the universe outside would be racing ahead. Gravity doesn't just pull objects, it controls time itself. The black hole was actually made by me and my friend for the school science fair, and this eventually got selected to the sub-district level, and it got A grade in both sub-district and district level. And this process was really fun, and we actually did very simple steps with a complex concept behind it. So if you like this project and this video, please share this video to someone else who's looking for a science exhibition project or just loves astronomy. And don't forget to hit that subscribe button and like button, and please drop your opinion on the comments about this black hole's model. So see you in the next video. Until then, it's me Archit signing off.